So with our basic definitions of rotational quantities, we can write down a set of rotational kinematic equations. And these should all be very, very, very familiar. Now let me just preface this by making a couple different columns here. Again, I'll write down the translational equivalents first, and then I'll write down the rotational equations. All right, in both cases, we are going to be dealing with, when we're dealing with rotational kinematics, you can only apply these equations if A is constant. All right, so don't forget that. The equivalent in rotational land is alpha is constant. All right, and in the translational world, we have a set of equations that we've grown to love. I'm just going to write them down in any old order. V is equal to V naught plus AT. X equals X naught plus VO T plus 1/2 AT squared. X equals X naught plus 1/2 V naught plus V times T. And last but not least, V squared is equal to V naught squared plus 2A delta X. All right, those are all equations that you've seen a million times by now. Right? So we can write down rotational analogs. Same thing, just change the letters, make them Greek. So we're going to have omega is equal to omega naught plus alpha times T. We're going to have theta is equal to theta naught. That's kind of ugly. Theta naught plus omega naught times T plus 1/2 alpha T squared. We're going to have theta is equal to theta naught plus 1/2 omega naught plus omega times T. And then finally, we're going to have omega squared is equal to omega naught squared plus 2 alpha delta theta. Okay? So the equations, again, I can't state enough, they're identical. We're just changing variables. You treat them in exactly the same way. And the beautiful part of this, because our values already sort of take into account the rotational sense of motion, you're never going to have to deal with a 2D kinematics problem in rotation. We're only going to be dealing with 1D rotations, which means that the object is rotating in a plane. All right? That's all accounted for in here. That's why we go through the process of doing this, because when we treat the objects that's rotating in the rotational sense, it allows us to eliminate the complexity of a 2D problem. You could certainly solve it using these equations. If I just have a simple object doing some rotation, I could certainly solve that using these equations. I could solve for the x position and y position, but it's a heck of a lot more complicated because now I'm really dealing with two sets of equations as opposed to one set of equations. All right, so it seems like a proper time to do an example. All right, so the example, do I dare it? Do I risk it? Can we get the text tool, please? I know you're going to spin, and then you're going to, yes, success. All right, so the example is this. You and a friend, you're at the carnival, and you're going to jump on the spinny thing. You're going on the spinny ride. This is different than the spinny thing that you'll see at the park. The spinny thing starts at rest and accelerates. That doesn't look right. At 0.1 rads per second squared. If the arms on the spinny thing have a length of 5 meters, I want to know how long will it take until you are traveling at the speed of sound. All right, so the spinny thing at the carnival, just the big, it's a big pole and you spin around it. I don't know, it's like the swing ride, right? Kind of like the swing ride. A simple version of the big swing that goes in a circle. So just in a very generic, basic sense, you're attached to the blades in the helicopter. So here is you being attached to the blades. All right, and of course it wouldn't be any fun if you could only have one person on at a time, so there's multiple people. Doesn't really matter. All right, and this thing is rotating about this axis, like so. The speed of sound is a good question. Does anybody know what the speed of sound is?
304.
Huh? Who?
340.
Yeah, about 340. It depends on temperature and pressure and things like that, but about 343 is the number that we typically use, meters per second. All right, so I want to know how long it takes so you get to that speed. All right, so this is a kinematics problem. Because we're accelerating at a constant rate, alpha is equal to 0.1 rads per second squared. All right. I want to know how long it takes to get to this speed. I start at rest. V naught is equal to 0. And the thing I'm looking for is time. All right, so I've got one problem here. The first problem that I have is, well, I've got this speed. It's actually in meters per second, but I want to deal with rotational quantities. So I need to know something about how does this relate to a rotational speed. Any ideas on how I might find out how that relates to a rotational speed? What the rotational speed is? So I know V, I want to know what omega is. Simultaneous yawning. Awesome. 2 pi r over t. What is 2 pi? It's one complete rotation, right? So in your case, 2 pi is one rotation, so it's like theta, and t is not little t, it's what? Big T. So that is one way to do it if you know big T. But we don't know big T, we know little t, or we want to know little t, and we actually can include that somewhere else. So really what 2 pi is theta, all right? That's just the angular displacement. And we could use any displacement. It doesn't really matter. And then we multiply that by r. Okay, so the 2 pi r over t, that actually comes sort of from this equation where 2 pi is, what it is. All right, so in this case, just like our equation for arc length, we related arc length to an angular displacement using using the radius. It's the same thing for velocity, and it's actually the very similar thing for acceleration. Okay, so in this case, we know v, and we want to figure out what. I'm sorry, this isn't theta. So I was saying one thing and writing another. So 2 pi theta over t is going to be a velocity, an angular velocity, an angular speed. So the translational speed is related to the rotational speed by the radius. All right. So in this case, we know the translational speed v sub s. We want to know what omega is, so we just rewrite this as omega is equal to v divided by r. All right. So we have 343 meters per second divided by r is, what did I say, 5 meters? That seems right. My meters cancel out, so the units here are 1 over seconds. And like I said before, that's good because radians are funny units. We don't really count those. So that's exactly right. If you do that, our goal rotational speed is 68.6 radians per second. All right, that's it's moving, obviously. Okay, so now we have all the information that we need to solve this problem. So up here, the other thing that we know is omega. I'll just add it to my list of knowns. That came from there. So I know Omega final, I know omega initial equals 0. I know that I'm accelerating at a constant rate. I want to know time. So if you go look at your list of equations, you'll notice that I think the first one that we wrote down said something like omega is equal to the initial omega plus alpha times time. So we can solve this for time. And it looks like that. So that's easy enough. On the numerator, I get 68.6 radians per second minus 0, because omega naught is 0, divided by alpha, which was, what, 0.1 radians per second squared. All right, so what we get is 686 seconds.